Hello, welcome to my class. We are discussing diffraction. We have seen the definition of diffraction and then the types of diffraction, Fraunhofer diffraction and Fresnel diffraction. Initially, we have started with the explanation of Fraunhofer diffraction, and we have saw diffraction due to single slit. And we need to see diffraction due to circular aperture, diffraction due to double slit, and then diffraction due to grating. We are following a procedure while discussing all these topics. First of all, we are seeing what is the aperture, whether it is single slit or double slit or circular aperture, how the aperture is, what is the design of the aperture, and then we are deriving the path difference conditions on the screen to note where maxima and minima occurs in that diffraction pattern. And then we are plotting an intensity curve for that particular diffraction phenomena. We have followed these three steps while discussing diffraction due to single slit. ముందుగా diffraction aperture ఏంటిది, ఆ aperture నుంచి path difference ఎట్లా క్యాలిక్యులేట్ చేసి ఇంటెన్సిటీ ఎట్లా క్యాలిక్యులేట్ చేస్తాం, అంటే ఆంప్లిట్యూడ్ క్యాలిక్యులేట్ చేసి దాని నుంచి ఇంటెన్సిటీ ఎలా క్యాలిక్యులేట్ చేస్తాం, ఆ తర్వాత ఆ ఇంటెన్సిటీ యొక్క కర్వ్ ఏ విధంగా ఉంటుంది. ఈ మూడు స్టెప్స్ లో మనము diffraction గురించి చెప్తున్నాము. We have discussed diffraction due to single slit. Now we are moving to discuss diffraction due to circular aperture. Let me share my screen. Yeah, this is Fraunhofer diffraction at a circular aperture. This is our next topic. You can observe the image which you see on the screen is exactly same as it is while we discussed diffraction due to single slit. Diffraction due to single slit, there we call this AB. Let me use annotation tool to show you where I am spotting. Yeah, yes, this one is AB. This is spot. This is single slit in the previous topic. Now we are calling this as circular aperture. Let me explain you what is this circular aperture. Slits are always slits are not parallel lines. In majority of cases, we see circular apertures, circular hole in the passage of light. Due to that hole, we observe diffraction pattern at some distance. Or in other words, while we are using optical instruments, just like microscopes or telescopes like that, binoculars, for magnifying any image, we use lenses, thin convex lenses, concave lenses, like that. We use a set of lenses in the construction of optical instruments. For example, if you consider a convex lens, all the points having same thickness forms a circle. All the points having same thickness on a convex lens will be a circular. This acts as a circular aperture for the incoming waves. So this topic, Fraunhofer diffraction at circular aperture, having major relevance in practical approaches while we use lenses, these instruments. So we need to study the diffraction due to this circular aperture. Let me show you. This is the circular aperture, and as we said earlier itself, W dash is a plane wavefront which is incidentally normally on the slit, and if at all the slit is not there, these waves will trace this path without deviating any angle. It traces this direction normal to the slit. This is a converging lens. We are arranging screen here. Screen is located in the focal plane, that is the distance between this lens and the screen is a focal length. So this lens, characteristic of this lens is it focuses all the rays which are reaching at the same angle at a particular point. You see these these undeviated wavelets all reaching at a point PO. I'm considering the point A and point B in the slit. There are number of points, n number of points between A and B. We discussed this all this in while discussing single slit. Okay, but now I am considering only point A and point B. The wavelet coming from A traces this path. The wavelet coming from B traces this path. These both are equal geometrical. These both are geometrical length is equal. So there is no path difference. Hence, at point P0, we observe central bright fringe. It is no issue. But due to this slit, this circular aperture, there will be a deviation. It is shown in dotted lines. There will be a deviation of angle. I am considering the deviated wavelets of deviated by an angle of theta. All the wavelets which are deviated by an angle theta. Okay. In those wavelets, I am considering wavelet coming from A and wavelet coming from B. Okay, these wavelets are reaching at point P1. We need to know what is the type of fringe at point P1, whether it is bright or dark. We can say only if we calculate the path difference of the waves coming in this direction theta when they reach point P1. To calculate that path difference, we drawn a perpendicular to this wavelet coming from A. It cut this line at point C. So the path difference is AC. The path difference between the wavelets coming from A and B is AC. AC. This is these two lines, these dotted lines AB and BC are perpendicular to these two lines. AB is perpendicular to this normal line and BC is a perpendicular to this line. So the angle between these two also becomes theta. So the path difference is from that figure, the path difference AC is equal to AB sine theta. AC is equal to AB sine theta. We used geometrically, we calculate the path difference. It comes out to be AC is equal to AB sine theta. I am saying the width of this circular aperture as D. Width of circular aperture AB is equal to D. So we derived the path difference. It comes out to be D sine theta. D sine theta. It is similar to the discussion of single slit diffraction pattern. So we can directly say if this d sine theta is equal to m lambda, their minima occurs, and d sine theta is equal to m plus 1 lambda by 2, their if d sine theta is equal to m plus 1 lambda by 2, there we get secondary maxima. Secondary maxima. Here m is equal to 1, 2, 3. For minima, d sine theta is equal to m lambda, m is equal to 1, 2, 3. But m is not equal to 0, because if m is equal to 0, there we saw principal maximum. I'm not going to the discussion of all these things. These all have discussed in the single slit diffraction itself. From there, I am taking these results. When d sine theta is equal to 0, there 0 means m is equal to 0. Then 0 multiplied by lambda 0. If d sine theta, this path difference is equal to 0, their principal maxima or central bright fringe forms. It is clear. Then if m is equal to 1, 2, 3 like that, then we see minima. Between these minimas, we see secondary maxima. The secondary maxima are formed at d sine theta is equal to m plus 1 lambda by 2. Now the thing is, all the points here, AB is a circular slit. In this slit, all the points having same distance. Suppose between A and B, let me show you. We have number of points. We have n number of points between A and B. So far we have considered only A and B, but if we consider any 2 points and the distance between these 2 points, all the points having same thickness will be circle. As this is circular aperture, as this is circular aperture, all the points, if having same distance between those 2 points, if we find the locus of those points, we get a circle. That is why we get, let me show you the pattern observed in single slit diffraction. This it will be like this. If m is equal to 0, d sin theta is equal to 0, then central bright ring. This ring is known as Airy's disk. This central bright fringe measurements were calculated first time by Airy, so it is named after him. This ring is known as Airy's ring, and this is first minima, second minima, third minima. Between these successive minima, we get second order maximas. These maximas are known as Airy's rings. Airy's rings. This is the diffraction pattern observed when we use single slit. Yeah, the diffraction pattern in the observed when we used circular aperture is central bright disk known as Airy's disk, surrounded by alternate bright and dark concentric rings. These rings are called as Airy's rings. Now we are going to calculate the angular radius of this Airy's disk. Angular radius means, if you see, this is the pattern observed on the screen. What I am doing is, from the lens, all the wavelets coming in this angle are forming this ring. Okay, now this angle, I'm going to calculate this angle. From lens, these wavelets are coming, right? The distance between lens and this screen is focal length. We already know that one. Okay, using this, I am going to derive this angle. Okay, angular radius of Airy's disk. Airy calculated this as theta is equal to 1.22 lambda by d. Now what we are trying to do is we will calculate theta is equal to lambda by d. How? Because from this condition, when theta is very small value, we can say d sin theta is equal to theta, then it becomes d theta is equal to m lambda. If m is equal to 1, that means first order minima. For first order minima, this equation becomes d theta is equal to lambda. From there we can say theta is equal to lambda by d. Theta is equal to lambda by d. But from figure, just now we saw the figure, like again I am showing you this angle theta is equal to, if we call, this is the x from center to this bright fringe, this is the x, and this one is f, and this one is x. This angle is theta. So using that, we can say sin theta is equal to x by f. From figure we can say theta is equal to x by f. Then x by f is equal to, that means theta calculated using the minima condition, theta is equal to lambda by t, and from figure theta is equal to x by f. So if we equate both of them, we get x is equal to f lambda by d as a radius of the Airy's disk, which is very closer value to the practically calculated value by Airy, that is 1.22 f lambda by d. This is about diffraction pattern due to circular aperture. Now we need to know what is resolving power. It is also known as limit of resolution of an optical instrument. Let me show you one thing to explain this. Here I am drawing a dot. Adjacent to that dot, I am drawing another dot. You could say these two as one. There are two dots. If I ask you how many dots I drawn on the screen, you say two dots. If you go a distance of 5 meters from the screen, you may see two dots. Furthermore, if you go beyond that distance up to 20 meters, you cannot see two dots separately. You can see only one dot. మనం దూరం పోతా ఉంటే ఏమవుతుంటదంటే వీటి మధ్యన చాలా తక్కువ స్పేసింగ్ ఉంది కాబట్టి చాలా దూరం పోయినప్పుడు ఏమవుతుందంటే మీకు ఇది ఒక డాట్ లాగానే కనిపిస్తుంది. 20 meters 30 meters దూరం పోయినప్పుడు చాలా దూరంలో ఉన్నప్పుడు ఒకదాని లాగానే కనిపిస్తుంది. దగ్గరికి వచ్చినప్పుడు మాత్రమే రెండు డాట్స్ లాగా కనిపిస్తుంది. డాట్స్ కాకపోతే ఒక లైన్ తీసుకోండి. ఈ లైన్స్ తీసుకోండి. చాలా దూరం పోయినప్పుడు ఇది ఒకటిలాగా కనిపిస్తుంది. ఒకటిలాగా కనిపించినప్పుడు మనం ఒక బైనాక్యులర్ లేకపోతే ఏదో ఒక ఆప్టికల్ ఇన్స్ట్రుమెంట్ యూజ్ చేసినాము. లెన్సెస్ తోటి జూమ్ చేసినాము. కెమెరాలో జూమ్ చేస్తాం కదా, అట్లా జూమ్ చేస్తే మళ్ళీ ఒకటి కనిపించింది, రెండు కనిపించినాయి. అంటే బై యూజింగ్ అన్ ఆప్టికల్ ఇన్స్ట్రుమెంట్ వీ కుడ్ ఏబుల్ టు సీ డిఫరెన్షియేట్ టూ లైన్స్ సెపరేట్లీ. దట్ ఈస్ ద రిజాల్వింగ్ పవర్ ఆఫ్ దట్ ఆప్టికల్ ఇన్స్ట్రుమెంట్. Ability of an optical instrument to produce a distinctly separate image of two objects located very close to each other is called its resolving power. Based on the మనం అంటుంటాం కెమెరాలో రిజల్యూషన్ ఎక్కువైంది, రిజల్యూషన్ తక్కువైంది అని చెప్పేసి. రిజల్యూషన్ అంటే రెండు డాట్స్ దగ్గరగా ఉన్నటువంటి రెండు డాట్స్ ని ఎంత దగ్గరగా ఉన్న వాటిని వేరువేరుగా చూపగలుగుతుంది అనే దాన్ని ఆ ఇన్స్ట్రుమెంట్ యొక్క రిజాల్వింగ్ పవర్ అంటాము. సపోజ్ 1 millimeter దగ్గర 0.001 millimeter దగ్గర ఉన్నాయి రెండు పాయింట్స్. ఆ రెండింటిని మన నేకెడ్ ఐ తోటి మనము సపరేట్ గా చూపలేకపోతున్నాం. బట్ మనము ఒక ఇన్స్ట్రుమెంట్ కెమెరాలో ఉన్నటువంటి ఒక ఇన్స్ట్రుమెంట్ యూజ్ చేసి ఎక్కువ రిజల్యూషన్ తోటి పెంచినప్పుడు అది సపరేట్ గా చూపెట్టగలుగుతుంది. అంటే వీఆర్ యూజింగ్ సమ్ లెన్సెస్ ఇన్ దట్ ఆప్టికల్ ఇన్స్ట్రుమెంట్. దోస్ లెన్సెస్ are able to show you these two objects separately. That is the resolving power of that instrument. The ability to show separate images of two objects closed very, very close. That is resolving power. Okay, actually when we use lenses or optical instrument to see separate ఈ రెండు లైన్లను మనం ఒక ఆప్టికల్ ఇన్స్ట్రుమెంట్ చేసి చూసినప్పుడు నిజానికి మనం అబ్జర్వ్ చేసేది ఏంది అంటే ఒక 30 meters దూరం నుంచి ఇక్కడ గీసినటువంటి రెండు లైన్లను అబ్జర్వ్ చేస్తున్నాం మనము. వాట్ వీఆర్ అబ్జర్వింగ్ ఈజ్ వీఆర్ అబ్జర్వింగ్ ద డైఫ్రాక్షన్ ప్యాటర్న్ ఆఫ్ దీస్ టూ ఇమేజెస్. ద డైఫ్రాక్షన్ ప్యాటర్న్ బికాస్ వీఆర్ ఎంప్లాయింగ్ lenses in that optical instrument. We are employing lenses. As we employing lenses, these lenses produces the diffraction image of this line as well as diffraction image of this line. We are not seeing directly these two lines. We are seeing the diffracted images of these two lines through two lines through that optical instrument. So to give a criteria for the resolution, Rayleigh gave a criteria. That criteria is known as Rayleigh's criteria of resolution for any optical instrument. This criteria is to show two objects separately by any optical instrument. The diffraction pattern must follow this criteria. This criteria is if this line diffraction is some pattern, principal maxima, first order maxima, second order maxima, like this. I am showing intensity curve of this line. Similarly, intensity curve of this line is also principal maxima, first order maxima, second order maxima, like this. For an instrument to see these two lines as separate, Rayleigh said it is a minimum requirement that the principal maxima of one object must fall on the first minima of the second object. This is the minimum condition. ఇప్పుడు ఇక్కడ చూపెట్టిన నేను ఫస్ట్ మాక్సిమా సెకండ్, ఇక్కడ ఒక ఇంటెన్సిటీ కర్వ్ చూపెట్టినా, ఇక్కడ ఒక ఇంటెన్సిటీ కర్వ్ సపరేట్ గా చూపెట్టినా. ఇట్లా సపరేట్ గా ఉంటే సపరేట్ గా కనిపిస్తాయి లైన్లు, పర్లేదు. అంటే ఈ లైన్ డైరెక్ట్ లైన్ చూడడం మనము దాని డైఫ్రాక్షన్ ప్యాటర్న్ చూస్తాము అని, ఎందుకంటే మనం ఇన్స్ట్రుమెంట్ యూజ్ చేసినాం కాబట్టి. దీని డైఫ్రాక్షన్ ప్యాటర్న్ ఉంది, దీని డైఫ్రాక్షన్ ప్యాటర్న్ ఉంది. ఇది దీని ఫస్ట్ ఆర్డర్ మాక్సిమం, ఇది ప్రిన్సిపల్ మాక్సిమం, ఫస్ట్ ఆర్డర్ మాక్సిమం, సెకండ్ ఆర్డర్ మాక్సిమం. ఇది దీని ప్రిన్సిపల్ మాక్సిమం, ఫస్ట్ ఆర్డర్ మాక్సిమం, సెకండ్ ఆర్డర్ మాక్సిమం. దీని ప్రిన్సిపల్ మాక్సిమం అట్లీస్ట్ దీని ఫస్ట్ ఆర్డర్ మాక్సిమం తోటి కోయిన్సైడ్ కావాలి, అయినప్పుడు మనకు సపరేట్ గా కనిపిస్తాయి. అట్లా కాకుండా దీని ప్రిన్సిపల్ మాక్సిమం రెండు కోయిన్సైడ్ అయినాయి అనుకోండి, అప్పుడు we couldn't able to differentiate these two lines as separate. We see only single line. This is Rayleigh's criteria. Let me show you a picture to get clear understanding of this Rayleigh criteria. You see here, you see this is principal maxima of one object, this is principal maxima of second object. These two are separate, so it is clearly resolved and we see two separate lines. Here you see in the dotted lines, principal maxima of one object overlapped with the principal maxima of the second object. You see dotted lines. Then we cannot say those two are separate lines. We see intensified image, resultant intensities increases and we see it as a single object. This is Rayleigh's criteria, minimum requirement. ఇక్కడ మినిమం రిక్వైర్మెంట్ కంటే ఎక్కువనే ఉంది రిజల్యూషన్. ఫస్ట్ దీని ప్రిన్సిపల్ మ్యాక్సిమం సపరేట్ గా ఉన్నాయి, క్లియర్ గా ప్రాబ్లం లేదు. ఇది మినిమం రిక్వైర్మెంట్. ప్రిన్సిపల్ మ్యాక్సిమా ఆఫ్ వన్ ఆబ్జెక్ట్ ఫాల్ ఆన్ ఫస్ట్ మినిమా ఆఫ్ ది సెకండ్ ఆబ్జెక్ట్. ఇది ఫస్ట్ మినిమా చూడండి, ఈ ఆబ్జెక్ట్ యొక్క ఫస్ట్ మినిమా ఇది. ఈ ఫస్ట్ మినిమా ఆఫ్ సెకండ్ ఆబ్జెక్ట్ ప్రిన్సిపల్ మ్యాక్సిమం దగ్గర ఉంది, సెకండ్ మినిమా దీంట్లోకి రాలేదు ఇంకా. ఇట్లా ఉన్నప్పుడు మనం అట్లీస్ట్ సపరేట్ గా చూడగలుగుతాము. దట్ ఈస్ Rayleigh's criteria. Once again I am going to show you the definition of Rayleigh's criteria. Two sources are resolvable by any optical instrument when the central maximum in the diffraction pattern of one falls over the first minimum in the diffraction pattern of the other. అంటే ఒక దాని ప్రిన్సిపల్ మాక్సిమం లో రెండో దాని ఫస్ట్ ఆర్డర్ మినిమం పడింది కాబట్టి రెండో సెకండ్ ఆబ్జెక్ట్ కూడా సేమ్ థింగ్, వైస్ వర్సా కూడా పాసిబుల్ అవుతుంది. దిస్ ఈస్ Rayleigh's criteria for resolution. Again we will discuss about resolution when we are going to discuss diffraction due to grating. Now we are moving further, that is Fraunhofer diffraction by double slit. Fraunhofer diffraction by double slit.